the story is pretty much the same for all interpretations. So quantum Zeno's paradox. So the story begins with Zeno himself. So here's the ancient Zeno paradox. So Zeno of Elea was like 2,500 years ago or so. He was a Greek philosopher, and he claimed that motion and time cannot exist because they are inherently paradoxical notions. And in order to prove this, he formulated several paradoxes. So one ancient author wrote that Zeno had like 20 different paradoxes. I think only 5 or so of them are actually known, are reported to us. This one is mentioned by Aristotle. So here's the paradox. It's called the paradox of Achilles and the torches. So Achilles, that's a character of ancient Greek poet Homer, around 3,000 years ago. Achilles is known for being a fast runner. He competes at a race against the torches, an animal that is known for being very slow. So, of course, you say Achilles wins. But now the torches gets a head start, 10 meters, let's say. Actually, the numbers don't play any role. So Achilles is 10 meters behind, and in order to win, he first needs to pass by the torches. Now, the claim is that Achilles, contrary to what you would have thought, Achilles will never pass the torches. And here's the argument. Suppose Achilles is 10 times faster. Again, the numbers don't really matter. You can do this story with any numbers. Now, when he has finished the 10 meters that the torches was ahead to begin with, then the torches will have completed another meter. Now, Achilles has to do another meter. When Achilles is done with that, the torches has added 10 centimeters, and so on. When Achilles has done these 10 centimeters, the torches has another, there's another centimeter ahead, and so on. So the torches is always ahead. Ask me a question. Okay. Okay, I mean, I guess nowadays nobody is persuaded by this paradox anymore. Everybody thinks, oh, yeah, Zeno, you're just making a mistake. So here's a comment by mathematician Hvar in his 1980 math textbook on analysis. Basically, Zeno could not believe that an infinite series could converge. So, maybe you could view it 2 different ways. For one thing, basically Zeno's argument points out that there are infinitely many points in time between time 0 and the time at which Achilles passes the torches, which is 100 divided by 9 meters. Or another way, Zeno had the idea that if you have an infinite sum, then the value of the sum has to be infinite. And now this is a convergent series, a geometric series. Here's the value. Good. Now, quantum Zeno's paradox. It's called quantum Zeno's paradox because it has something, some flavor of being a paradox about time or about motion. The name was actually coined by Misra and Sudarshan in 1977, who proved, well, in their paper, they didn't actually discover the phenomenon, but they gave a mathematical proof that it actually exists, that it is a correct consequence from quantum mechanics, under a rather weak and general assumption. So other people had before kind of studied special cases, and they had, in their paper, they gave a kind of general version of that phenomenon. So this phenomenon is often called the quantum Zeno effect, because it is an actual effect. It is something that actually happens as a consequence of quantum mechanics. This effect, or this paradox, whichever way you want to look at it, was discovered by Alan Turing, known as a founding father of computer science. It was discovered kind of he discovered it shortly before his death. The paradox comes up from the attempt to compute the probability distribution of the time at which a detector clicks. So let me talk about this physics question about the time at which a detector clicks. So that's like asking for a Born rule on a time-like surface. Now we have a Born rule on for a constant time. So that's what I mean by a horizontal surface in space-time. So constant time in one particular frame that corresponds to a horizontal surface. And then you ask, okay, if I measure the position of my particles at this particular time, what's the probability distribution? Let's say here I wrote it down for a single particle, what's the probability distribution? It's given by psi squared, so that's the Born rule. You could also ask a corresponding question for curved surfaces. Yeah, I mean, Matthias had a lot of curved surfaces in his talk already. Let's say it's a space-like surface, not necessarily horizontal, it could be curved. Also here you can ask, if I place detectors along the surface everywhere, then what's the probability distribution of where I find the particle, or if I have several particles, the probability distribution of the configuration in which I find the particles. So that would be the configuration would then be, if it's an n-particle system, then the configuration, I guess, would be a point in similar to the n, or maybe you want to, well, I guess it depends on whether you have labeled or unlabeled particles, maybe you want to symmetrize that. Good. So now the obvious guess for what the probability distribution on a curved surface would be is the following. So the density here, V of D3x means now the surface element, the three-dimensional infinitesimal surface element. V of D3x means the invariant volume. That would be the volume relative to the metric on the surface. So expressed in terms of the metric, this gives you a factor of, so in coordinates it would be the coordinate volume times this the square of the determinant, whatever. Then there's a formula for that. And that's kind of the natural analog of psi squared. You see some psi bar psi here. And you see the gamma mu, so that's essentially the component of the current J mu that Matthias talked about, orthogonal to that surface. So U is the future unit normal vector to the surface at that point. Okay, so there is some natural answer to that, and in this paper we give a proof that, well, assuming Born's rule and the collapse rule on horizontal surfaces, we prove that also on these curved surfaces, this is actually the probability distribution that you get, which is the kind of the thing that which is the natural guess for the probability distribution, because it's the natural analog of psi squared. Good. Now the arrival time question. Now we're considering a time-like surface. So for example, you place a detector somewhere and have it wait for the particle to arrive. Or let's say the detector is a surface, the particle can arrive at an arbitrary time at the surface. You ask, okay, what's the probability distribution of this arrival time? You could ask this question for the relativistic or non-relativistic case. The rest of this talk will just focus on the non-relativistic case. But so the main reason I'm mentioning the relativistic setting is there you see how the question actually amounts to asking, oh, if I have a time-like surface, three-dimensional surface in four-dimensional space-time, then yeah, that's and if you ask, okay, where will the particle arrive on the surface? Yeah, that's the question of waiting for the particle to arrive. So this would be the setup. We have, let's say, many little detectors. These are like our surface elements, so this means like a little detector. We have some, so in this example, I've just assumed that the detectors don't move, so it's fixed in time, so this surface is really vertical. We have some region omega here that is surrounded by the detector surface, and the initial wave function of the particle is prepared somewhere inside. I've just symbolically indicated that here, it's somewhere inside. And then And then sooner or later, one of these detectors will click, and this result will be then shown, let's say, by some pointer, whatever. Okay, so then we can ask the question.
What is it? I don't.
You're unhappy that.
No, I don't understand exactly what you mean by this picture. It's a space picture, or is it a time picture?
Okay, no. This is just in space.
Everything in space.
Everything in space, no time here. The
wave packet is moving,
the wave packet is moving, so I start with some initial wave function, and then it can move, it can spread, whatever. It will evolve, and then I ask, when and where does the particle arrive at the surface? So I have put detectors along my surface. I ask which detector will click. So the question where does it arrive then corresponds to the question which detector clicks. And one thing in this picture, I've shown both the start and the end of the experiment. The start of the experiment, because here I'm showing the initial wave function, and the end of the experiment, because here I'm showing already what came out, what comes out in the end.
And do you have a description of your detector?
I'm coming to that. Okay, so here I'm presenting the question, the problem. Good. So there will be a time and a place where the particle will be detected. Let me call the time capital T, the place capital X. So together they form kind of a space-time point of detection. That will be capital Z pair T comma X. So here kind of something in formulas. So omega is the region that is surrounded by detectors. It's some subset of R3. You could also take a half space, so it doesn't have to be, it doesn't have to have finite volume, doesn't have to be surrounded. It could be the outside of some surface. The initial wave function, we would suppose, has to be a function concentrated just in omega, and the detecting surface would be the boundary of omega. So d omega means the boundary. Then there's also, so that we want to have the probability distribution for the Z, and since there might be positive probability that the particle will never be detected, let me also introduce some formal symbol for the event that the particle never gets detected. So I chose here this infinity symbol if no detector ever clicks. And now we want to compute the distribution of Z from the initial wave function. So this is what we ask a Born rule. By the way, this is different from computing in Bohmian mechanics the time and place at which the particle first exits omega in the absence of detectors. It makes a difference whether you have presence or absence of detectors. In the absence of detectors, it's easy to compute this point and this time by just solving Bohm's equation of motion. That is, you have this region here in space, omega, you have your Bohmian particle. It moves around, you solve the equation of motion up to the point when it touches the surface. That's the time of arrival at the surface. But that assumes the absence of detectors, and actually the presence of detectors makes a difference here. Jean?
Can you say briefly why? Because I always thought that was the problem.
I'll come to that.
Okay.
Okay, so that's why actually the common phrase time of arrival for this question is a bit ambiguous, because in Bohmian mechanics you can also speak about the time of arrival and its probability distribution also in the absence of detectors. So, and there's no question what it is. You just solve Bohmian mechanics for that, you work it out. But now I'm asking a different question. What happens in the presence of detectors? What is the probability distribution of the detection event? So that's why I call it time of detection. So I mean, the first hurdle, the obvious hurdle here is that quantum mechanics does not know a self-adjoint time operator. Okay, so what do you do? How do you compute this? Okay, there have been various proposals for that. So here's several works about this question that I want to mention briefly. So Pauli in 1958 had a paper in which he explained why there is no time operator, because he argued it would have to be canonically conjugate to the Hamiltonian. That means the commutator between the time operator, if there were such a thing, and the Hamiltonian would have to be IH bar, then you show that if the Hamiltonian is, if the spectrum is bounded from below, then, which is the case for usual Hamiltonians, then such an operator doesn't exist.
Why would they have to have this kind of mutation relation?
Well, I guess Pauli asked the question.
I know this.
Can't you have a time operator? And then kind of classically, time is in some sense canonically conjugate to energy, like position and momentum, and then you would have a commutation relation, canonical commutation relation between them. Okay, so that was Pauli's argument for saying such an operator doesn't exist. Now that leaves open the question: how do you compute this distribution? Aharonov and Bohm, I mean, they did many works on different questions. So they also have a paper on this question of time of arrival, they called it. So that is kind of around the same time, just 2 years after the famous Aharonov-Bohm paper that Lev showed us earlier today. So their proposed algorithm was to compute the classical time of arrival. So, for example, let's say for a half space, if omega is a half space, and now you talk about arrival at a particular plane, say x1 is equal to 0. That defines a plane in three-dimensional space. So initial x's, let's say, are negative, and now the particle is coming. The detecting surface is x1 equals 0. Now, the idea is, well, you could compute classically the time of arrival, give a formula for it. Now, classical, the following would happen. I guess I have to draw a picture here. So here's the x1 axis. Okay, so here's the plane, x1 equal to 0. So here's our half space omega. Now a particle is coming here, and if you know it's, well, there's no potential here, so if you know its position and momentum, you can compute the time at which it arrives at the surface. Okay, here's the formula for that. Then quantize the formula. Now in this case, you have to you have a function of position and momentum, so it's not obvious how to quantize that. Okay, so they had a proposal for that, do it in a kind of symmetric way. Then you have this product of three operators that's formally self-adjoint. There are actually mathematical, technical difficulties of the kind that this doesn't directly define a self-adjoint operator. Whatever, that was the idea. You quantize the classical formula, then you get some time of arrival operator. It's a kind of nice idea, a nice guess, but actually, since the argument has basically nothing to do with how detectors work, it doesn't actually sound very convincing that this would give you the right statistics. Alcock in 1969 considered complex potentials as models of soft detectors. A soft detector would be one that has a certain detector volume and that allows the particle to travel in this detector volume for a while before it gets detected. A hard detector would be one that detects a particle immediately as it enters the detector volume, and a soft detector may take a while and may sometimes miss a particle. Now, as I will describe later, actually complex potentials are nice and useful models of soft detectors, but in the end we're actually interested in the case of the hard detector. Kajdowski had some further proposal. Assume there is a self-adjoint arrival time operator T, and then he talked about properties that this operator should have, symmetry properties, made axioms for that, and then identified which operators actually satisfy these properties. So that also leads to some operators, at least in this special situation where omega is a half space where you have many symmetries. Of course, in the general situation, you don't have any symmetries to work with, so it's unclear what to do with this approach in that case. Levens in 1996 discussed the distribution of the time at which the Bohmian trajectory arrives on the boundary in the absence of detectors, but as I mentioned before, that is not necessarily the same thing as the distribution of the time of arrival in the presence of detectors. Okay, so I said Turing was asking the question and arrived at this Zeno paradox. So let me discuss how he did that and how the problem arises here. So for simplicity, let's focus on the case where omega is a half space, although the reasoning also works with any shape. And so the surface here is a plane. The plane x1 is equal to 0, the same as I mentioned before. So the initial wave function here is completely in the left half space. Now the idea is the following. Make an instantaneous ideal quantum measurement of the event x1 is greater than 0. So that means the observable here would be the indicator function or characteristic function of the event x1 equal to x1 greater than 0. That is the projection to all functions that are concentrated in the right half space. Now, so the idea is this. Let the particle run freely for some time, tau, and then make a measurement of whether it's in the right half or in the left half. If it's in the right half, you say, oh, the particle has reached x1 equals 0, actually already gone beyond, and so the detector should click now. And if it's in the left half, we let the particle continue and say, oh, we haven't detected it yet at the detector surface.
But again, this is not taking into account the presence of the detectors.
The idea here is the following. You do that at time tau, then you do it again at time 2 tau. So if you don't detect the particle, if the measurement of this right half space observable doesn't say +1, then you say you haven't detected the particle yet. And you do it, you repeat it at times 2 tau, 3 tau, at regular time intervals tau. So instead of having a detector weight here, you do these kind of repeated ideal quantum measurements of an observable you know. Now you don't have to worry about time operators that you don't know. This observable you know completely. You know how to compute this, and you do it kind of repeatedly. And of course, you want to make the tau small. You want to check very often, very quickly, every millisecond, or I don't know what, when the particle is there. So ideally, you want to take the limit tau goes to 0, and that's what Turing had in mind, how to compute this probability density. The problem is that when you do the computation, you find that in the limit tau to 0, the probability of ever finding the particle in the right half space becomes 0. And this is called the quantum Zeno effect. So it seems that any concept of an ideal detector is impossible. And Misra and Sudarshan summarized this whole phenomenon by the nice slogan, "A watched pot never boils." Well, that surely sounds paradoxical because, well, I'm pretty sure watched pots do boil. Okay, I can actually explain to you.
No, because when it
I can
starts
actually-
boiling, you take it off the fire. No, because when it starts boiling, you take it off the fire.
Yeah, here it would be the same situation. When the particle arrives, you detect it, you stop the experiment. Okay, so here is a derivation of this effect. Here, in the simplified version, I will do the calculation in a two-dimensional Hilbert space. And here, so now the wave functions have two components, and the first component is the left half, and the second component is the right half. Okay, so with each of these half spaces, I just associate one dimension. So I start out in the left half, now I evolve with some Hamiltonian that will not preserve whether it's in the left half. So I chose here some Hamiltonian, so this is actually the first Pauli matrix, some Hamiltonian that will rotate the thing. So if I just let this unitary time evolution roll, then starting from being purely in the left half, it will rotate into the right half. So after some time tau, for example, it will have a non-zero component in the right half. Okay, so now after time tau, I want to interrupt the unitary evolution by a quantum measurement of something that has eigenspaces left half and right half. Okay, so for example, the third Pauli matrix. So now eigenvalue -1, that would be the outcome for particle detected. +1 would mean particle not yet detected. Good. Now I let this experiment. I do my measurements at time n tau, and now I follow this experiment up to some fixed time capital T. So tau becomes small. So the number of collapses will be capital tau divided by capital T divided by tau. Good. Now the claim is that the probability that any of these measurements yields the result -1, which means particle detected, tends to 0 as tau tends to 0. And the computation is actually pretty easy. You figure out what the unitary evolution is. So you start with this initial vector, and now you evolve it with this Hamiltonian, and here's the answer. The first component is cosine of tau. The second component is -I times sine of tau. So you see that it moves out of this of the first subspace. Okay, and in particular, if you wait until tau is equal to what do we need, pi over 2 or something, it will have completely moved over into the right half. Good. Now then you measure sigma 3. So the probability of okay, so let's now consider just one time interval of length tau, the first of these ideal measurements. Okay, the probability of no detection during this, at this first measurement, that means the probability of eigenvalue +1, that means no detection. Yeah, what is it? It's the psi squared of the first component here. The first component is cosine tau, so it's cosine squared of tau. So, and if this eigenvalue comes out, then the state vector collapses back to this to the eigenspace of sigma 3. That means back to 1, 0. Then it evolves from 1, 0 to this thing again. We do the same experiment again independently. Probability cosine squared of tau. That's the probability of not detecting the particle, and then it collapses back. So the probability of no detection in m consecutive trials is cosine squared to the power n. Good. Now let tau go to 0, and m will then go to infinity, so that m tau tends to the given constant capital T. So m is essentially constant over tau. And then the following happens. This probability p here, then some math shows that p actually converges to 1. Here's an easy way of seeing that. Cosine of tau, you see here's the second order Taylor expansion of the cosine. It's 1 minus tau squared with a factor of 1/2. And if you take this 1 minus tau squared to the power 2m, then you see you get this expansion. And here the m is like 1 over tau. So you have a tau squared here, 1 over tau. So one factor tau cancels, other factor tau remains. Here, this is like also like n squared. You get 1 over tau squared times tau to the 4. Factors of tau remain. So all these terms here have factors of tau in them. They all tend to 0. So what remains is the 1. Or let me put this differently. The probability of detecting the particle here is sine squared of tau. So that is small like tau squared. So in every single attempt to detect tau, to detect the particle, you have a probability of order tau squared to detect it. And how many attempts do you have to detect it? You have 1 over tau attempts. 1 over tau is the number of attempts. Tau squared is the probability of success in each attempt. So this is of order tau. So as you let tau go to 0, this quantity goes to 0. So this is then your probability of finding the particle. Oh, much pot never boils. Just in the right moment. How can you do that?
Wasn't watched closely.
I think it's coming back. Is it? No, okay, very good. Now, so in addition to this paradox, there's another paradox that goes back to Alcott. That goes in the same direction, kind of impossibility to have a hard detector to detect the particle as soon as it arrives. So Alcott started from soft detectors. So let me say a few words about these soft detectors. The idea is that a soft detector can be modeled by an imaginary potential. So let's consider again the case where omega is the left half space. And now, as a model of the situation, Alcott considered the one particle Schrödinger equation, just for this one particle. So the detector is not described as an n particle system. Its defect is just included here as this potential. The idea is you put here an imaginary potential. So the potential is 0 in the left half space, where the particle can move. And in the right half space, you put an imaginary potential. Here, V is a positive constant. So this is purely imaginary. Now what will happen if you, well, usually in quantum mechanics, of course, your total potentials are real. Never put an imaginary number in potential, because then something bad will happen. Here's what will happen. When you derive the continuity equation, you see that that in addition to the usual terms, which are the minus divergence of the current, you get a further term which has a definite sign, so that so that means here, since we have this indicator function here, it means that term is 0 on the left half, and it's a negative constant on the right half. This negative constant is minus 2v over h bar. So that means that we're constantly losing probability. And that, well, what that means is perhaps most easily visualized by means of the Bohmian trajectories. There you would have a particle, it can move in the left, it can cross over to the right-hand side, and at any time where it's in the right half, it has a certain rate of disappearing. It has a probability of disappearing. So this disappearance here is interpreted as the particle has been absorbed because it has been detected. And as long as it hasn't been detected, it doesn't disappear, but continues moving there. And then the rate at which it will be absorbed or disappear is this 2v over h bar. So this is the rate of loss of psi squared. So then in this picture here, the norm of psi will not be constant, it will not always be 1, it's shrinking. It's at time 0, it starts at 1, and then shrinks until it reaches 0. Or maybe it takes an infinite time until it reaches 0. So in particular, this time evolution here, the Schrödinger equation with this complex potential is non-unitary. But that's not bad here, that's exactly what we want. Because if you visualize things again, I mean the same is true in other interpretations, but if you visualize it in terms of a Bohmian particle, then the probability of the particle being in a certain volume at any time t is then actually given by psi squared. So the norm squared of psi is the integral of psi squared. So that's the probability of the particle being anywhere at time t. So that's the probability that the particle has not been detected yet, that the particle is still around. So that makes sense that this is a number between 0 and 1. Okay, so that's Alcott's model for an ideal, for a soft detector.
Does it really ever reach 0, or it goes to 0 every time? in the large time limit?
Well, I guess this also, let's see, presumably it doesn't reach zero in finite time. It takes an infinite time to reach zero. Okay, now here's the paradox. Alcock reasoned in the following way. Now I know how to model a soft detector, and now for a hard detector, all I have to do is make it less and less soft and make it harder and harder. So that is, I change the detector so that it will be faster and faster for detecting the particle. Yeah.
Sorry, what I find counterintuitive, so this rate is independent on the form of the wave function.
Yes, it is. So if you make it a constant, so if in the potential, if you make the potential a constant to the right hand side, then yes, this rate is independent.
Because it's okay. So in this,
you could also make it x dependent or so. Then kind of the detector would be stronger in some regions than in others, and kind of detect the particle more easily or more quickly in some.
Okay, so in this one, the particle is always in the detector. So this is
no, the particle starts out in the left half space. Because the initial wave function originally is in the left half space, so psi squared distribution is all in the left, and then it moves around, crosses the plane, enters the detector region, and then after a while,
so could you maybe say with the symbol 1? So it's 1 is
okay.
the projector on
Yes,
this half
so,
space.
Yes, so this symbol means either 1 or 0, means 1 or it's a function of x.
So it's a
means
function of
1.
x. Okay, I get it. Okay.
And if this condition is not satisfied.
Okay.
So this is really a notation for this function here. Let me draw it.
Projection of.
Yes, so you could accept a
As a
characteristic function of the positive numbers or indicator function of this event, or multiplication by this function is a projection operator in Hilbert space, and it projects to the subspace of wave functions that are concentrated in the right half space.
But Jan asks that it doesn't depend on the wave function. It does depend on the wave
So
function.
it's like the expectation
It's
value.
an operator, it doesn't depend on the wave function. What do you mean it's
The
a projection
rate.
operator?
The rate of detection depends on the wave function.
Yes.
So it's in all cases
okay.
it goes to
Yeah,
0,
let's
but
see.
it's different with in a different way.
So I think what you wrote, because it actually depends on the coordinate x, so it's like it is like the expectation value of the projector with respect to the psi maybe.
So I think if I understood the question correctly, here what I wrote is the rate of the particle to be absorbed or to disappear, and you could ask what's the rate of detection. So here's the slight difference. So if I know that there's a certain probability of the particle being here, then the number of detection events will be proportional to that probability if for every single particle the rate of being absorbed is constant. So that is like, okay, the fighter airplane is going over enemy's territory, and then kind of every minute you have a constant probability of being shot down. Okay, now depending on how many airplanes are coming here, then the number of airplanes that are shot down per minute, of course, depends on that, it's proportional to that. Okay. Good. So, here's Alcock's reasoning. So once the particle has entered the detector region, and it might leave the detector region again, who knows, but once it has entered the detector volume, the average lifetime of the particle, that is the average time until detection, until being absorbed, is, well, the inverse of the rate. So it's h bar over 2v, where v is this constant in the potential. Okay, so his approach was, I take a hard limit. I let this lifetime shrink to 0 by taking v, the strength of my imaginary potential, the strength of my detector, to infinity. Now then the following difficulty appears. So in this limit, it turns out that at any time t, the wave function will be 0 in the right half for all t. So the particle never gets detected. It never enters the right half. What happens in the limit is that a wave packet arrives at the surface and gets reflected at the surface perfectly. 100% reflection, 0% transmission.
Again, in the limit.
In the limit, yes. So Alcock wanted to derive the probability distribution for an ideal hard detector. Again, an ideal hard detector. This limit doesn't give you any reasonable answer. What happens in the limit? It becomes equivalent to a Dirichlet boundary condition, which will force the wave function to be reflected at the plane x1 is equal to 0.
Is it different from your previous work?
It's different in the sense that you mean, is it different from Turing's attempt? Well, Turing had this idea of repeated ideal measurements, and now Alcock has this situation. There's nothing repeated here. It's all the time, continuous in time, and it has this imaginary potential. Okay, so at least, well, anyway, both approaches lead to the same conclusion, the same impossible conclusion.
So I misunderstood. The first thing I understand, you let it in and then you test it. This is a physical process. It's mathematically can be described like this. But I don't understand how you, I don't know how to put imaginary potential. Only what's selected, effective potential, is imaginary. So if you do this kind of thing, and then you look, then you get this mathematics. But there is no, I'm not aware of any store where I can get device which imaginary can be plugged.
Okay, so for you it may be obvious that these two pieces of mathematics lead to the same conclusion. To Alcock it was not obvious, to me it was not obvious, but it is true nevertheless. Both reasonings lead to the same conclusion: the detector never clicks. And so Alcock's paradox is in line with the quantum Zeno effect. Also for Alcock's paradox, I wanted to present a derivation in a two-dimensional Hilbert space. Let's say here again, the first dimension is the left half, the second dimension is the right half. We start out completely in the left half. Now we evolve the state vector with this non-self-adjoint Hamiltonian, which in addition, you see the 0, 1, 1, 0, that was the self-adjoint part of the Hamiltonian, the same as in the example before. That's free evolution across the surface to the other side. And here on the right-hand side, I added an imaginary potential. Okay, now you consider the time evolution with this non-self-adjoint Hamiltonian. And then it is in fact true that in this limit v to infinity, psi t, at any fixed positive time t converges to psi 0, the 1, 0 vector, the vector in which you have the particle completely on the left-hand side at any time. I thought I could do the calculation here in the talk, but then I tried to do the calculation and it becomes complicated, so I won't do it. Okay, does actually quantum mechanics make any prediction at all for this question when the detector clicks? Or maybe I should say first, I mean, obviously you put a detector there, you wait for the particle to arrive. Sooner or later the detector does click. So the question is, what's the correct mathematical description of that?
Well, depending.
Wait, let me finish. Okay, so and can you actually get a prediction for that from quantum mechanics? Because in quantum mechanics you don't have a self-adjoint time operator. So how would you even start getting a prediction from quantum mechanics? Well, here's a way how you could get a prediction. Although quantum mechanics does not provide a self-adjoint time operator, it makes an unambiguous prediction for the distribution of z, the pair t, x, though in an unorthodox way, kind of the way of thinking how a Bohmian would think of it. You model the detector as an n-particle system, and you solve the Schrödinger equation for the big system formed by the particle, the object that we want to detect, and all the detectors. And let's say maybe I will need also to include in the system a clock and a recording device constructed so as to keep a record of which detector clicked when. Then we get this big superposition, as in the measurement problem, as with Schrödinger's cat, a superposition of different detector states and different records of this recording device. And at some late time t, we make a quantum measurement of the record. And then this superposition, let's say, collapses, and we get we read out the record, we get one of the answers. Now the record says, oh, detector number 5 clicked at 3 o'clock. And then we say, okay, that is what happened. Detector 5 clicked at 3 o'clock, and so that is RZ. And then you can, in principle, compute the distribution of Z.
This when.
Okay.
When is a clock. You have to describe the clock because
yeah, that's what I'm suggesting to do here. You have a physical clock. You have n particles that include a clock. You solve the Schrödinger equation for all the particles, so you of all people should be happy. So then at a late time, I read out the record. Good. So that's a way of extracting some prediction for this experiment from quantum mechanics. Now, of course, to do that in practice is a hurdle because you would need to solve the Schrödinger equation for 10 to the 23 particles. So you don't want to do that in practice. Well, one conclusion that you can already draw is that the distribution of Z is given by a problem. A problem, positive operator value measure. You see, a measure in mathematics is a function that associates with every set some number. For example, the probability distribution can be expressed as a measure. For every set, every event, it gives you a number between 0 and 1. So measures, they have to be additive. That is, when you consider the union of two disjoint sets, then their numbers add. Likewise now, instead of numbers, the values are positive operators. So for every set, you get a positive operator. And when these sets are mutually disjoint, then their values add. So the value of the union is the sum of the values. And it's normalized like a probability measure. So this script Z would be the whole space. So now the value for the whole space for a probability measure would be 1. Here it's an operator, it's the identity operator, the 1 operator. So that's what a positive operator value measure of problem is. And kind of the key fact about problems is that you can prove in great generality that for an arbitrary experiment, the statistics is given by some problem. Statistics given by a problem means the following. If you do the experiment on some arbitrary initial wave function psi 0, then your probability distribution, the probability distribution is a measure, so it gives a number between 0 and 1 for every set delta. And here's how you compute this number. You take this positive operator, you sandwich it with between the wave function, and that gives you a number between 0 and 1. Why is it greater than 0? Because this operator E of delta is positive. Why is it less than 1? Because if you add another positive operator, complement of the set delta, you get the identity operator, so its eigenvalues cannot be greater than 1. Okay, so this in fact gives you a probability measure then, and it's a general fact for arbitrary experiments that the distribution of the outcomes is given by this kind of problem. So here, at least, we know that there exists a problem that gives us the right statistics. Now, of course, we'd like to compute this problem in a practical way, at least approximately, have some kind of Born rule that allows us to compute this without solving the Schrödinger equation for 10 to the 23 particles. Now, the correct problem, the one that you get from solving the Schrödinger equation, will depend on all details of the detectors, including their quantum states at time 0. Now, our hope or expectation is that there is a particular problem, E0, let me call that, or maybe E kappa, depending on one or a few parameters kappa, and the cloud of different problems that you would get from different initial quantum states of the of the detectors that is a good approximation and that can be expressed by some simple rule. So that would then represent an ideal detector. So all real detectors would be close to the ideal detector, but the ideal detector could be described by a simple rule on a single page, a formula or something. And now I will describe actually a proposal for that, a particular problem, the kappa that could be taken to be an ideal detector, and in fact an ideal Hvar detector. So despite all the paradoxes that suggest that ideal Hvar detectors don't exist, I will tell you how in fact it is possible. So what pot does boil after all, although the quantum Zeno effect is for real. I'm not saying there's any mistake by Turing or Mizrahi and Sudarshan. The quantum Zeno effect is for real. It is actually true that if you do these repeated measurements, you get zero probability, but there's a different way of doing it that will give you a non-zero probability. And maybe let me explain it before we go into the discussion. So here, this proposal, I call that the absorbing boundary rule. And the rule says the following. So now this is the rule for how to compute the probability distribution of the detection time and place. You solve the one particle Schrödinger equation. So this simple recipe now involves just one particle Schrödinger equation as opposed to 10 to the 23 particle Schrödinger equation. But you solve it with a boundary condition, and here's the boundary condition. It looks kind of similar to a Dirichlet boundary condition. A Dirichlet boundary condition would be the same thing with 0 on the right-hand side, but it has a non-zero term on the right-hand side. Actually, one still calls it a Dirichlet boundary condition if it has some real factor, but this one has an imaginary factor on the right-hand side. So this is a condition that, that is required at every boundary point, where n of x is this unit normal vector to the boundary. Kappa is some constant that characterizes the detector. And it is a mathematical fact that you can solve this Schrödinger equation with this boundary condition. Now, this boundary condition implies that the probability current always points outward. That means the component of the probability current in the direction of n, that is in the outward direction. Well, since now I'm just plugging in the n into this formula for the current, now I'm using this boundary condition, so I can replace this n dot derivative with the normal derivative in the outward direction. I can replace it by I kappa, so I can compute what the imaginary part is. It's constant kappa times pi squared, so it's non-negative. So that means when you solve this Schrödinger equation with this boundary condition, and the current is always pointing outward, that is, the wave function is constantly losing weight. So it's again a probability, it's a time evolution that's non-unitary, and psi, the norm squared, the norm of psi is constantly shrinking. It starts at 1 and goes down, perhaps down to 0, maybe down to 0 only after an infinite time. Okay. Now the rule here is that that the probability of detection is exactly given by the amount of current, of probability current that flows in that time interval dt into that surface interval d2x, and that is here. This is the current density of that. Okay. And in addition, we could state that if the experiment is not completed, if it gets interrupted at a time before the particle was detected, yeah, then we also have a collapse rule. The wave function then afterwards, you stop the experiment, then you carry on with this particle in a different way, then will exactly be this psi t that you have obtained from this time evolution, but then you have to normalize it. Okay, some properties of this time evolution. The norm squared is again the survival probability, the probability that the particle is still there at time t. So here capital T was the time of detection, and lowercase t is any time at which you're looking at this particle. So that's a decreasing function in t. that's because the particle gets absorbed when it gets detected. This time evolution is not unitary, the Hamiltonian is not self-adjoint due to loss of probability at the boundary, but it's well defined by some math theorem. Actually, the time evolution then forms well, not a unitary group, it forms what's called a contraction semigroup on this Hilbert space. The skew adjoint part of the Hamiltonian is negative operator. The Hamiltonian is actually not necessarily diagonalizable. If it is, then its spectrum lies in the lower half plane, whatever. These are just math details. And in Bohmian mechanics, the particle, now it's also easy to say what the Bohmian trajectory for this particle would be. You started with a psi-square distributed initial condition, and then it moves according to the usual equation of motion, and then at some time it hits the boundary, and that is exactly the time at which it gets detected. So the detectors on this boundary, on the surface, just detect the particle when it arrives and where it arrives. And then the particle gets absorbed. Now for this quantity, if you take that as the detection time, then you actually get an energy-time uncertainty relation. I mean, there's a lot of literature about energy-time uncertainty relations, largely because it's not so clear what you mean by time of what. So here you have a particular time, the time at which the detector clicks, and you can ask, is such an uncertainty relation true? And it is actually true. You can prove that. Oh, Jean.
But so, in the end, you are solving the problem you mentioned at the beginning, namely looking Bohmian mechanics when the particle goes out, except that now your wave function also shrinks.
Now the wave function is not the same wave function as it would have been in the absence of detectors. You know, the wave function in the absence of detectors, it evolves unitarily, doesn't respect this boundary condition, but this one, now I have a different evolution for the wave function. It does respect this boundary condition, so it's a different wave function now. So the presence of the detectors has an effect there.
What is the support of the psi t? Is it still
Always the omega.
Always
So-
an omega.
Yes, so everything that reaches the boundary and goes out, I discard that. Then it becomes easy to write down what actually the problem is that is associated with that. So here's what the formulas look like for those who understand these kind of formulas. So it actually defines a problem which depends on this parameter kappa. So this is a problem defined on this space of possible outcomes of this experiment, and these operators act on this Hilbert space. This problem is not a PVM. PVM means projection value measure. So if your positive operators in the problem are always projection operators, then you call it a projection value measure. Now every self-adjoint operator is associated with a projection value measure on the real axis, which just corresponds to the eigenspaces of the self-adjoint operator. So for a general problem, you don't have that, and as a consequence of that, you have no eigenstates of detection time in this framework in which the detection time is given by the absorbing boundary rule. And for this slide, I want to give some qualitative argument for why one should expect this absorbing boundary rule to give the right result. But since it's already late, let me skip that. Let me skip this overview of literature. One point that I should perhaps emphasize is, while the particle, the Bohmian particle, always gets absorbed exactly in the moment when it hits the boundary, this is not the same with the wave function. When a wave packet hits the boundary, it will get partly reflected and partly absorbed. And here is actually a graph of how much of it will get absorbed depending on the wave number k compared to this constant kappa. So there's a particular wave number or particular energy at which the detector is most efficient and actually absorbs 100%. Near this energy, it will absorb nearly 100%, but for very small energies or very large energies, the detector, this model of detector will actually turn out to be inefficient and not absorb the incoming wave packet, or not all of it, not much of it, but reflect much of it. It's a consequence of this fact that the presence of detectors actually changes the Bohmian trajectories even before they reach the boundary. That is because some part of the wave function may reach the boundary before the particle, because the particle is somewhere in the wave packet and the wave packet spreads out. And then the first part of the wave packet already gets reflected from the wall and then will influence the further motion of the particle before the particle has reached the boundary. Yes, Kaushik.
Yeah, in the detection machine, are we considering this reflection of the wave? Because like you say that when we are considering the boundary, we are just we are not considering the wave packet that has been transmitted through, like outside the boundary condition. But what about the inside one, the reflected wave?
Yes.
So like, are all those properties that you just described same for the reflected one also?
So what happens to the reflected wave? It will go back inside and then evolve further there according to the Schrödinger equation. Maybe it will reach another boundary on the other side. They will be partly absorbed, partly reflected, and so on. So it goes back in and evolves there according to the Schrödinger equation.
I mean the properties are same for the reflected one also?
I'm not sure which properties you have in mind.
The properties that you just described, like.
Okay, so the whole wave function. So, for example, the property that the size of the wave function shrinks, the norm, the integral of psi squared, and that's because part of the wave function gets absorbed when it reaches the boundary, and part gets reflected, stays inside, and only the part that stays inside that's counted in this norm here. Okay, everything that goes outside is discarded. Let's see. One can easily set up a lattice version of the same thing. And then one can easily explain how this approach actually avoids the quantum Zeno effect. Well, the quantum Zeno effect is for real. Now here I describe it on a lattice. So we have lattice sides at space points epsilon, 2 epsilon, 3 epsilon. That was on the previous slide, so here's the lattice. Okay, and now the quantum Zeno effect occurs when I take this limit t to 0. I keep my epsilon constant, and the number.
What's epsilon?
The lattice width. This distance here between two lattice sides, that's the epsilon. And n is kind of 1 over epsilon, the number of lattice sides. If I keep the n constant and the epsilon constant, I get the quantum Zeno effect. But there is a different limit in which I actually avoid the quantum Zeno effect. For this limit, you have to coordinate tau and epsilon in such a way that tau over epsilon cubed becomes neither 0 nor infinity, but stays in between. Of course, this you wouldn't have guessed that. So this is something that you can figure out from hindsight. After you know which result you want to get in the limit, you find out a way of obtaining this result in a limit. But of course, Turing could not have guessed that, and so it's no wonder that Turing arrived at the quantum Zeno effect. Something similar happens with Alcott's limit of soft detectors. Let me skip the details here. Thank you very much for your attention. John was first.
Before we start with the discussion, could we open the windows, the curtains? That's very dark. Thank you.
I think John was first.
Well, but maybe there are students who want to ask questions first.
Okay.
But may I just
No, you are
really
the
because I'm pretty sure that Zeno effect works, and it's not supposed to be detected. What can you tell me in your model is your precision of detection, the time precision of your detection, is it finite or it goes to zero? Because I believe that if you have clock which is goes to this, which its precision goes to zero, this detector will never detect anything. So you have some other detectors, these detectors, you said that when, it's written when. So when, written with some time precision. Everything is physical. So if this precision will go to zero, it will never be detected. And this all what I know about Zeno effect. I don't think you can override it by any sophisticated mathematics. Or if you can say that if you consider soft detectors which are not really very precise, then you can have a regime in which you detect it. And the real detectors are not infinitely precise.
So
infinitely precise detector will never detect. Will never detect.
So first of all, I don't deny the existence of the quantum Zeno effect. The quantum Zeno effect is a fact. What the quantum Zeno effect means is if you do these ideal measurements of whether the particle is in the right half repeatedly at short time intervals, then the probability of ever finding the particle goes to zero. Now in this model, in this description, the precision is perfect, so you get a real number. So it gives you, for the probability distribution of the detection time, it gives you a continuous distribution. So the detection time and the detection place are continuously distributed. In this model, wait. In this model, the detectors are constantly waiting at the surface, and there is no rhythm to this.
But may I ask, I will spend billions of dollars and present a delta function which is very, very energetic, with very delta function in wave packet, very, very close to delta function, which is time resolution of arrival of this wave packet to your detector with infinite, unlimited precision. Will your detector tell me in this which moment it will be detected? I will know when it will arrive because it's very short. This your wave packet is wide. I will send very, very sharp one.
Okay.
So can you tell me with which precision? There will be some moments that you'll say that the precision of the clock of your detector should be. You say it's infinite. It will tell me exactly that the time of arrival. It will send the delta function.
Yeah, you have in mind. I want to prepare a state where this distribution becomes a delta function. So one of the mathematical statements here is since this distribution is given by a problem, and since this problem is not a PIVM, it doesn't have eigenstates. That means that there is no quantum state for the particle for which the distribution of the detection time will be a delta.
No, I said I said Gaussian.
Okay,
Gaussian with a very short width. I don't have delta function.
So you have in mind now that in space this function is a delta function. Maybe let me draw it here. Very, very narrow wave function. So it moves, let's say, in this direction, and it's very narrow.
It will not be. It will be wide, but when it will come to the boundary, it will be like this.
Okay. Yes. So we can
arrange
this way.
I arrange it that when it's come to the boundary, it's extremely narrow Gaussian. Extremely narrow. It will pass this path with as time as small as I will. If your clock can tell me exactly the time, this kind of detectors will not detect the normal wave function.
Okay, so let's look at this. So we have some Gaussian wave packet. It moves towards the boundary. It actually becomes narrow as it comes to the boundary.
Yeah.
At the time when it reaches the boundary, it becomes a delta function.
Yes.
Now, what happens?
Not almost. Yeah. Very short.
Okay. So what happens here? Let's see. Let's go back to this plot here. You know that the detector has efficiency 100% at a particular energy value, and it's kind of bad at very low or very high energies. Now, a delta function, of course, has extremely high energy, or if you close to a delta function, you still have very high energy. As a consequence of that, only a small part of the wave function will actually be absorbed and detected, and a large part will be reflected, because this detector has only a certain energy range. Let's say here, where the efficiency is close to 1. So what will happen is that some part of it will be absorbed, but maybe not so much. If it's kind of ideally a delta function, then very, very little. The rest will be reflected. So then it will be reflected. Okay, maybe I use a different color. Now it comes back. The reflected part, it will. It will spread again. Then at some point it will reach the other side. Oh, now it's.
This is not the.
Let's see.
No. The question.
Maybe it's more manageable here, and then.
No. The question is when it will arrive. Will it? Sometimes you say it will detect. Yes. You say it will not be efficient.
Yes.
But you say that sometimes it will detect.
Yes.
Will it will give me exact time?
Yes, it will give you an exact time.
Then I don't. It cannot work. But maybe.
Okay. Other questions?
Well,
Questions from students? Okay.
they are tired already. So, no, I have a stupid question. Can you do an experiment? Can you check that? Can you see that experimentally, or it's impossible?
I don't know.
Why can't you detect? I mean, you detect particles in the double slit experiment, so.
I don't know. Maybe in many experiments, you're basically in a scattering regime, which is kind of your wave function has become locally a plane wave, and it doesn't matter so much how hard or soft your detector is. So, for example, what people use in accelerators, where they detect particles, they use scattering theory, which means that they are kind of far away from the particles. The particle travels a long time. The wave function becomes locally a plane wave, and the detector is ideally soft, because you don't want to have reflection back from the detector. And yes, and then kind of it's a different question than this hard detector question.
Yeah, but I don't understand what's the point of all this exercise if you can't predict what you will measure in a laboratory. I mean, I naively thought the point of that was to make predictions. Well, when I talked to Detlef, I had this impression that they wanted to make predictions that go beyond what is done by ordinary quantum mechanics.
Maybe because you think the question should have an answer, and you want to maybe you think that the question should have an answer, and you want to figure out theoretically what the answer is.
Yeah.
Maybe you would expect a Born rule also to hold on a time-like surface. Maybe you expect that there should be a simple answer to the question, what is the distribution of arrival time? Now, it seems that these people that I mentioned, Pauli, Aharonov, and Bohm, and I mean, kind of, there are many people who made some suggestions and some considerations about how you might guess the arrival time distribution. Obviously, they all thought that there should be some simple way of arriving this at the correct values. Although it is in principle true that well, you always know that if you can solve the Schrödinger equation for 10 to the 23 particles, then you can always in principle compute it. But I guess all of these people believe that there should be some simple way. No.
So if I don't confuse something, I think there's experiments where you trap atoms and you might be losing your atoms. But you might also ask the question, is the atom there? And I think you can use that for stabilization of the cloud or something like this.
Okay.
Of the atomic cloud or of the atomic particles that you're trapping. But I'm not sure about exact references, but I think this is being used. Only that in an experiment we don't have the 2 quantum Zeno. I mean, you can use it to stabilize, but not completely hold it. So you
talk about soft detectors for some value experiment.
Yeah, I mean, but I think it's for experiment a little bit different because you cannot take the tau going to zero.
Mm-hmm.
That's you have to then compare including this kind of stuff as well.
Mm-hmm. Yeah.
So, just to clarify, so the standard quantum mechanics cannot, or there's no known approach to calculate this for hard detectors with the pulse going to, so delta T going to zero.
Well, I would say, I mean, this approach here doesn't depend much on whether it's standard quantum mechanics or Bohmian or anything. So I sometimes talk about the Bohmian particle, but this is kind of for illustration, so it gives an easy picture. It's nice to see what happens in the Bohmian picture then. But there's, nothing particularly. You could have the same absorbing boundary rule actually in a kind of Copenhagen framework. One guy who wrote about this was Einhard Bern. I think he was the first guy to ever write down this particular boundary condition, and he is a very Copenhagen guy. He hates Bohm.
Okay, so in this sense, but this is the only approach that can do this for hard detectors and delta tau going to zero in this sense. So
It's the only approach that I know.
okay, and then what would be the is Alcock's approach, for example, with the soft detectors, is this corresponds this to experiment? So if I say that an experiment, I would agree that in any experiment you have finite delta tau and you have in this end can never have a hard projection. Would you say that the other approaches model them derivative times correctly? Or is for example, is the Alcock approach consistent with this approach in the case where the detector is soft and okay, but this is continuous anyway? Yeah,
I don't really know about the experimental situation. I would suppose so, that for soft detectors that it fits. I would expect that.
Okay.
It fits what you see in the lab.
I heard the informal formulation of the Zeno paradox that if you measure a particle very often, repeatedly, in very short time intervals, then it gets frozen into place. So how does this, is this a correct description of the paradox? And if yes, how does it fit in with what you just
Yes. So here. So consider this example again, a two-dimensional Hilbert space, and now things evolve, and at kind of regular intervals tau, which are small, we make this quantum measurement. Then every time we make this measurement, the state vector jumps back to the original one. Okay, so it moves out just a little out of the original position, and then at the next measurement it moves back. So now in the limit in which we let tau go to zero, it's just frozen in this 1, 0 state. Yes, so this is exactly what you see here. It's frozen in this state, which kind of now, well, this happens if you project it to a one-dimensional space. Now here, if you say the left half space, then you project it to an infinite dimensional space, and then it could still move around in a non-trivial way in this half space of in 3 dimensions, or this infinite dimensional subspace of Hilbert space. Okay, maybe one last question.
So, if the wave packet comes to a boundary, there is a lot of discussion, papers, when there is arrival time, because it's not very clear. When extremely sharp wave packet comes to a boundary, everyone agrees when the particle arrives to a boundary. I understand, your detector will not tell us, because mostly it will not work. Am I right?
That is right. So it will give you the result that you expect with a certain probability, maybe a small probability, depending on how close you are at a delta function, and then it will be reflected and it will be then detected on the other side. Yes. So this proposal disagrees with some things that you might expect. Good. So maybe that was the last question for today. Thank you very much.